This video is for section 11.1, the chi-squared test. So the definition for a chi-square statistic is a measure of how far the observed counts are from the expected counts. The formula for the statistic is chi-squared equals sigma of observed minus expected squared over the expected, where the sum is over all of the possible values of the categorical variable. So to begin, we have an example about M&Ms. So Mars Incorporated reports that their M&Ms peanut chocolate candies are produced according to the following color distribution: 23% each of blue and orange, 15% each of green and yellow, and 12% each of red and brown. Joey bought a bag of peanut chocolate candies and counted the colors of the candies in his sample. He had 12 blue, 7 orange, 13 green, 4 yellow, 8 red, and 2 brown. Number 1 asks us to state the appropriate hypotheses for testing the company's claim about the color distribution of peanut M&Ms. So for number 1, you would have to say the null hypothesis is probability of blue, which is equal to 0.23, probability of orange, which is equal to 0.23, probability of green, equal to 0.15, probability of yellow, equal to 0.15, probability of red, equal to 0.12, and probability of brown, equal to 0.12. The alternative hypothesis would be that at least one of the probabilities for each color, so we're going to call it P sub i's, is incorrect, which just basically means that one of these probabilities that are here is not correct based on what's actually in the bag. 2 asks us to calculate the expected count for each color, assuming that the company's claim is true, and show your work. So what we would do, we see that blue and orange have the same probability, so we would say that the expected counts for blue and orange would be the same. So to find the expected counts, we would need to count up how many M&Ms were actually in the bag. So we would need to do 12 plus 7 plus 13 plus 4 plus 8 plus 2. Whenever we do that, we would get 46. So our expected for blue and orange, we would take the 46 that's definitely in the bag, and we would multiply it by the 0.23, which is the 23% that is supposed to be representative of blue and orange. So we would do 46 times 0.23. Whenever we do that, we would get 10.58. So then we see that green and yellow is the same, or should be the same, so we would do green and yellow together. When we did that, we would say 46, because that's the number of candies that were in the bag, and we would multiply that by 0.15, because it told us that they say that there's 15% of yellow and green. And when you do 46 times 0.15, you get 6.9. And then red and brown have the same probability. So I should expect to see the same number for red and brown. So I would do 46, that's the number in the bag, times the percentage that they say that the bag is of red and brown, which is 12, so times 0.212. And whenever you do that, you get 5.52. Three says to calculate the chi-square statistic for Joey's sample and show your work. All right, so if you are calculating chi-squared, what you're going to do is you're going to say, you're going to have one for each of these. So you're going to do a fraction that represents blue, fraction that represents orange, fraction that represents green, so on and so forth. So let's start with the blue. So if you would start with the blue, you would say, you'd have to look and see how many were actually in the bag. So the blues that were actually in the bag would be 12. So you would start with, on the top of the fraction, the observed minus the expected. We got our expected in question 2. So our expected for blue is 10.58. We square that over the expected. All right, now we would do the orange. So in the bag, he saw 7 orange M&Ms. So you do observed minus the expected, which was 10.58. You square that, and you put it over the expected. Then we would do green. So in the bag, there were 13 green M&Ms. The expected is 6.9, so 13 minus 6.9 squared over 6.9. Then the yellows. So in the bag, there were 4 yellows minus 6.9 squared over 6.9. Then you need to do the reds. So in the bag, there were 8 reds. The expected for red was 5.52. Square that over 5.52. And then in the bag, last but not least, was brown. So there were 2 in the bag that were brown, so 2 minus the expected for brown, which is 5.52. Square that over 5.52. So basically, you would take all of these, plug these into the calculator. When you did that, you would get 11.3724. Chi-square distributions are a family of distributions that take only positive values and are skewed to the right. A particular chi-square distribution is specified by giving its degrees of freedom. The chi-square goodness of fit test used the chi-square distribution with degrees of freedom equal to the number of categories minus 1. When the expected counts are all at least 5, the sampling distribution is close to the chi-square distribution. So there are a couple of things that you need to remember. The first is that the mean is going to be equal to its degrees of freedom. The second is for degrees of freedom that are greater than 2, the peak of the chi-square density curve is at degrees of freedom minus 2. So if I'm looking at, let's look at degrees of freedom 4. So the mean is going to be equal to the degrees of freedom. So if I look at that curve, I can see that the mean is probably somewhere around 4 because it is skewed to the right. And then I'm looking at the peak, and so if I look at the peak would be about right here, and that is at 2. And so if I think about that, if my degrees of freedom is 4, the peak should be at 2 because it should follow this degrees of freedom minus 2. So 4 minus 2 would give you 2, peak should be at 2. If I look at 8 here, 8 is also the degrees of freedom is 8, and that would make my center to be at 8, or my mean to be at 8, because it is skewed a little bit to the right. And then if I look at where the peak is, the peak seems to be about at 6, and that should make sense because my degrees of freedom is greater than 2, and so I should be able to say 8 minus 2 to get where my peak would be. So basically, when we talk about this goodness of fit test, this is what you're going to end up with, some sort of curve like this. And basically, it uses approximation to compare the observed sample with the expected probability distribution. On the goodness of fit test curve, or the density curve for that, you will have a p-value, and that is going to be the area to the right of chi-squared under the density curve of the chi-squared distribution with k minus 1 degrees of freedom. So basically what that would look like is if you had a curve that was like this line would be your chi-squared, and you would be finding this, and this would be your p-value. So the good news is you can find the p-value for chi-square tests on the calculator. So to do that, you would have to go to second bars. You would do option 8, and you would see something that looked like chi-squared CDF. You would then put in your chi-squared. You would then put in your upper bound. Your chi-squared would also, just to point out, be your lower bound. And the reason it would be your lower bound is because you're finding the area to the right of that chi-squared line. So that would be where you would begin, basically. And then your upper bound would be what you did next, and then you would have your degrees of freedom. So on the next example, we're going to continue with our analysis of Joey's sample of M&M's peanut chocolate candies from the previous Check Your Understanding. So number 1 said confirm that the expected counts are large enough to use a chi-square distribution. Which distribution, specify the degrees of freedom should we use? So for number 1, basically if we went back to where we worked out what our expected values are, we should see that all of our expected values are at least 5, and if they are, then we're good to use a chi distribution, or a chi-squared distribution. So we would say all counts, and let's say all expected counts, are at least 5. And so because all expected counts are at least 5, then we should use a chi-squared distribution with degrees of freedom equal to 5. The reason we use 5 is because we had blue, green, yellow, orange, red, and brown. So we had 6 colors. But remember to do degrees of freedom. You're going to say 6 minus 1 to get 5. Two, ask us to sketch a graph that shows the p-value. And so if we were doing that, we know we're using a chi-square distribution of degrees of freedom equal to 5. So we would have our curve. It would be right skewed because chi-square distributions are always right skewed. Our mean should be at 5. And our peak should be at 5 minus 2, which would be over here at 3. So then it might be useful to do like, of course this would be 0. So then you would have, let me fix this a little bit. So you'd have 0 here. You'd have 10, 15, and then so on and so forth. Now, we also found our chi-squared earlier. Remember that your distribution has a line, and you're finding the area to the right of that line, and that would be your p-value, but that line is your chi-squared. And so if we go back to that original problem where we worked it out, we found that our chi-squared was 11.3724. So that is where we would put our mark. So we would estimate about where we think 11.3724 is. So we would say it's maybe like right in here. And then this part here would be our p-value. And this would be chi-squared equal 11.3724. 3 asks us to use table C to find the p-value, but we're just going to do it on the calculator for right now. So we're going to go to the calculator. We are going to go to second vars, and we're going to go to option 8, which is the chi-squared CDF. Our lower bound is going to be where our chi-squared was, so 11.3724. Our upper bound is going to be infinity, so 1e99. And our degrees of freedom is going to be 6 minus 1, which is 5. So when we work it out, we get that our p-value is approximately 0.045. So p-value equals 0.0445. Number 4 asks us, what conclusion would you draw about the company's claimed color distribution for M&M's peanut chocolate candies? Justify your answer. So we would say, since the p-value is less than 0.05, we reject the null hypothesis and conclude that at least one of the proportions of a particular color is different. So more about the chi-square goodness of fit test. So suppose the random large sample size and independent conditions are met to determine whether a categorical variable has a specified distribution expressed as the proportion of individuals falling into each possible category. Perform a test of null hypothesis where the specified distribution of the categorical variable is correct, and the alternative hypothesis, the specified distribution of the categorical variable is not correct. We can also write these hypotheses symbolically using P sub I to represent the proportion of individuals that fall in category I. So this is like what we did in the beginning when we were first talking about the M&M's problem. Start by finding the expected count for each category, assuming that the null hypothesis is true. Then calculate the chi-square statistic. So we did that in step 3 of our original problem, where the sum is over the k different categories. The p-value is the area to the right of chi-squared under the density curve of the chi-square distribution with k minus 1 degrees of freedom, which we just did in the second example for the second check your understanding. And you are going to use the chi-square goodness of fit test when you have a random sample or a randomized experiment, a large sample size, so all your expected counts are at least 5, and when your individual observations are independent. When you're sampling without replacement, check that the population is at least 10 times as large as the sample, so that would be your 10% condition. All right, the next example has to do with biology. So biologists wish to mate pairs of fruit flies having genetic makeup dominant R, recessive R, dominant C, recessive C, indicating that each has one dominant gene R and one recessive gene, lowercase r, for eye color, along with one dominant C and one recessive C gene for wing types. Each offspring will receive one gene for each of the two traits from each parent. The following Punnett square shows the possible combinations of genes received by the offspring. Any offspring receiving an R gene, dominant R gene, will have red eyes, and any offspring receiving a dominant C gene will have straight wings. So based on the Punnett square, the biologists predicted ratio of 9 red-eyed straight-winged 3 red-eyed curly-winged, 3 white-eyed straight-winged, and 1 white-eyed curly-winged offspring. To test their hypothesis about the distribution of offspring, the biologists made a random sample of pairs of fruit flies. Of 200 offspring, 99 had red eyes and straight wings, 42 had red eyes and curly wings, and 49 had white eyes and straight wings, and 10 had white eyes and curly wings. Do these data differ significantly from what the biologists have predicted? Carry out a test at the alpha equals 0.01 significance level. Discussing that Punnett square was difficult for your statistics teacher. That is not my area. So on this one, we would start by having to state. So we would state what we plan to do. So we want to perform a test at the alpha equals 0.01 significance level. Of the null hypothesis when the probability of red-eyed straight-winged equals 9 out of 16. All right, now the reason I got 9 out of 16 is because here it said that they had 9 red-eyed straight-winged, 3 red-eyed curly-winged, 3 white-eyed straight-winged, and 1 white-eyed curly-winged. And so if I added all of those up, I would get 16. I know that there's 9 of them that have red eyes and straight wings. The probability of red-eyed and curly wings is 3 out of 16. The probability of white eyes and straight wings is equal to 3 out of 16. And then the probability of white eyes and curly wings is 1 out of 16. The plan. So we should use a chi-square goodness of fit test if the conditions are met. So the conditions we have to look at, first we have to look at, is it random? And so it says biologists make a random sample of pairs of fruit flies, so that's satisfied. The second is, do we have a large sample size? So to calculate that, we have to do what we expect each of the values to be. So let's do red and straight, and I'm going to represent that with RS. All right, so the probability is 9 out of 16. and the sample size, or the entire sample, was 200. So if I do 9 out of 16 times 200, I would get 112.5. Then I would do red-eyed and curly-winged. So that would be 3 out of 16 times the 200, 37.5. Then white-eyed and straight wings is 3 out of 16. Multiply that by 200, 37.5. And then white-eyed and curly wings would be 1 out of 16. Multiply that by 200. 12.5. So when I look at all of these numbers, all are at least 5, so that works. Next, we have to do independent. So when we do independent, we basically have to check and see that the 10% condition is met. And so to do that, we would basically do 200 times 10, and that would give me 2,000. So basically then we would say it seems reasonable that there would be more than 2,000 pairs of fruit flies. The next is due. So because we checked these conditions and everything seems to be met, now we should move on and actually do our chi-square goodness of fit test. And so we're going to do that on the calculator. Now to do this on the calculator, we're going to need to first go and put all of our information into a table. So we're going to do stat and then do edit. The reason we're doing all of this on the table is because we want to be able to have our observed and our expected side by side, and our calculator will do all the rest of the work for us. So our observed would come from here in this last little paragraph. So we had 99 red-eyed and straight-winged. We had 42 red-eyed and curly-winged. We had 49 white-eyed and straight-winged. And then we had 10 white-eyed and curly-winged. Our expected would come from what we just did when we checked to see if our sample was large enough. So our first expected should be 112.5. Our second, 37.5. Our third, also 37.5. Let me go back. And our fourth should be 12.5. We want to make sure too that these line up. So this row should all represent red-eyed and straight-winged. And this row should all represent red-eyed and curly-winged, and so on and so forth. So once we get that, then we can go to STAT. We go to tests, and this time we're going to go to the chi-squared goodness of fit test. So you're going to need to basically do the up arrow so that it gets you to like the end of the list, and you're going to do option D. So the chi-squared goodness of fit test. So your observed should be in L1, your expected in L2, and your degrees of freedom for this is going to be 3. The reason it's going to be 3 is because we had 4 different categories, so we would do 4 minus 1 to give us 3. Once you do that, then you should go to calculate, hit enter, and then it gives you your chi-squared, which is the 6.19, and it gives you your p-value. So you would say the test statistic is chi-squared equal to 6.189, and the p-value is 0.103 using degrees of freedom equal to 3. The next step is our conclude. So to conclude, we would say since the p-value is greater than 0.01, we're saying 0.01 because remember from the beginning of that problem, it said that we wanted to use a significance level of 0.01. So our p-value 0.103 is definitely bigger than our significance level of 0.01. We fail to reject the null hypothesis. So that means that we do not have enough evidence to reject the biologist's predicted distribution of traits in offspring.